Hello, everyone, and welcome to the Geek Narrator podcast. I am your host, Kaivalya Apte, and I'm back with another interesting episode on databases. Today, I have Heikki from Neon, and we are going to talk about Neon and the use cases. We'll also go a bit deeper into understanding the architecture and some of the internal details as well. So, I'm really excited. Thanks a lot for joining me, and let's start with a little bit of introduction.
Thanks for having me. So my name is Heikki Linnakangas, and I'm a self-taught programmer. I've been doing programming since I was a kid as a hobby first, and then working on databases throughout my career, really, and mostly Postgres. So I've been working on Postgres for the last 20 years now already, for different companies and with slightly different angles and different forks of Postgres and different areas. But most recently, since 2021, I've been working for Neon, which we co-founded back then.
Perfect. Yeah. Um, I typically want to start with understanding why something was created, and it would be awesome to understand from your perspective, like what is Neon and why it was created.
Right. So the point of Neon is to the separation of compute and storage. Like that's at the very heart of the architecture, and like all of the other stuff we do follows from that. So the original idea started from like looking at the architecture of Amazon Aurora. Like they were the first ones to do the separation of compute and storage for all TP databases. But there really isn't, and there wasn't like an open source version of that. So we got together with the idea of let's build an open source thing that does this separation of compute and storage. And of course, I've been working on Postgres for a long time, so I mean that's why Postgres, and it was the natural choice. But we started from that architecture, and what are all the things you can do when you have that architecture?
Absolutely. I also love Postgres. I've been working with Postgres since many years now. Of course, not really deep into the internals, but in different flavors, like sometimes from the application side, sometimes really figuring out why Postgres is not using my index and all those kind of weird problems. Postgres is amazing, and I love talking about it and the ecosystem and technologies around it. So let's get started. So when I was reading about Neon, it said like serverless database, like serverless Postgres database, and I really want to understand what does serverless mean when it comes to databases, and why is it game changing for these modern applications, especially talking about cloud deployments.
So serverless, it's a buzzword. Like people mean slightly different things with it, but there's some common themes. Um, And basically, if something is serverless, it means that you are thinking about a service rather than running servers. So you're thinking about connecting to the service and using a service, and you're not thinking about starting or stopping a server. You're not thinking about scaling RAM or choosing instance sizes and that kind of operations. It's more like a way of thinking. So not having to manage a server, like it's just there always. When you need it, it's there. That's the key of it. One part of it is pricing. Like it's when you have a serverless service, you expect it to be priced per use. It's like at a fine grain. So at Neon, we do pricing per compute hours and storage hours, like how many CPU hours have you consumed, when was the service running, and how much storage you're using. Like the more traditional model would be like you choose an instance size and then you pay for that, whether you use it or not. But with serverless, you want to be charged by only for what you use. And the kind of the scaling down to zero is a big part of that. At Neon, we scale down, we auto-suspend your compute when you're not using it. But also we make it very transparent to the user. So when you connect to it, we immediately spin it up again. There's only a small delay when you start it up. And it looks like it's always there, even though, of course, behind the scenes, there's always servers. So like when you talk about serverless, at the end of the day, there is always a server behind it. Like everything, the cloud is just a bunch of computers, data center somewhere. There's no way around that. But the point is that to the application developer, to the user, you don't need to think about those layers. They're abstracted away. And what you really have is a URL that you connect to. The database is a URL.
Interesting. Yeah. I've heard this term in different setups for different types of databases. And as you mentioned, it might be a confusing word for folks who think that, oh, where is my data going? When is it even accessible? But it's more like a billing mechanism for the vendors to make it more cost effective for folks. But when I compare these new use cases, for example, I want to experiment and just validate my idea and I need a Postgres database with all the amazing features. So I just go to Neon and try to create one database.
Mhm.
It's easy because it's fast. I can do it very easily. Uh,
Right.
So this is one use case, but then the next use case, which is I'm an enterprise, right? I already have my Postgres databases running, and I have a ton of traffic, and which is sometimes can be spiky, sometimes can be very constant. So when we talk about this serverless paper usage benefit, how does these two use cases compare?
Backing up a little bit, like even enterprise users actually care about the simple, make it super easy to set up a database and start running. Like all the benefits you get from Neon is the developer productivity. So enterprises actually care about that as well, especially if you have within an enterprise, you will have small teams and they have similar needs to individual developers and small companies as well. But for enterprises, another kind of an example is if you have a large fleet of small databases, that can be a pain to manage. And some of our bigger customers, partners, I can mention Retool. We made a case study recently. They have like hundreds of thousands of databases that they offer as part of their service to their users. It's a no-code app. If you want to build an application, don't need to write a lot of code. You can draw your widgets in the UI. But if you're building an application, you also need a database. Like you need to store the data somewhere, and that's why they partnered with us, and they're using Neon behind the scenes, unless you have some other place you want to run that. But for that kind of use cases where you have a large fleet of databases, it makes it a lot easier to manage them, and the cost savings really show up there. You don't need to have hundreds of thousands of VMs running all the time. You only have the ones that are actually actively used. And if you have a large fleet, probably not all of them are used at the same time, at least. But it's a lot easier when you don't need to manage all that. Neon will take care of that and launch the ones that are needed when they're needed.
Yeah, that makes sense. So it looks like developer productivity and cost are the two biggest reasons and common reasons why people choose serverless Postgres, something like Neon. Of course, developer productivity also adds to cost or cost optimization. But what are the other features when it comes to key features of Neon? What are some other features?
So I think we need to step back a little bit and look at the architecture, like the separation of compute and storage, because all of these features fall out of that architecture. So the basic idea is that we have a separate Neon storage system where all of the data actually lives. And then we run Postgres in a VM. Like everyone gets their own VM, like your own little sandbox where you run your own Postgres. But that Postgres is ephemeral. Like we launch that VM when you connect to your database, and we kill it after 5 minutes of inactivity, or you can tune it. But this separation allows us to do a lot of interesting stuff with the storage. First of all, that allows us to do that like cost savings, because if your database is not running, we can just shut it down. And when you launch it, we can spin it up very quickly because there is no data that you would need to move around or copy and so forth. Another thing it allows you to do is branching, and I think we'll probably come back to that later, but branching is a natural consequence of having a separate storage system that can support all of that. The third one is that in regular Postgres or other databases, if you want to have read-only nodes, if you want to have replicas, you have to actually make a copy of all of your data. Like you take a dump, a backup of your database, and you copy and you restore it somewhere else to initialize your replica, and then you start to do the replication. That can be ineffective if you have a large database. Copying around a lot of data is expensive. But more importantly, it's a lot easier to manage with Neon. So with Neon, well, you have one primary write node, which is regular Postgres streaming the write-ahead log to the storage system. But you can have as many read-only nodes as you want connected to the same storage system. So you don't need to copy the data. You can just have read-only instances, read-only Postgres nodes connected to the same storage. So that's a very efficient use of the resources, and it gives you a lot of flexibility. Traditionally with Postgres, people often set up also like a standby for high availability purposes. So you want to have a standby server running, which already has all the data. So if you need to fail over, that happens quickly. But there's a lot less need for that in Neon because the storage system itself is highly available, and we keep copies of the data, and we do all the high availability magic at that level. And that means that if for some reason the primary node dies, or you kill it, or it crashes, whatever, we can spin up a new one to replace it very quickly, like within seconds. So there's a lot less need to have a replica for high availability purposes.
Interesting. So you also gave like a brief overview of the architecture, like how storage and compute separation helps you. And then you have one primary writer, and then others are read replicas, and you can scale reads horizontally by having as many read replicas as you want. And then the storage layer is like completely separate. Um, You also mentioned about branching as a feature. So what does branching mean? And let's talk a bit about that as well. Like, how does it help in a real production environment?
So branching there's a few different ways you can use that. The first one is that it's actually part of our like backup and restore stories. So it's like the Neon storage system keeps all of the history of the data. And so it replaces your traditional backups and the write ahead log archive. Like you don't need to have that separately. It's all integrated in the storage system. So the storage system keeps all of the history of your data, or back to some cutoff point that you can define how much history you want to keep, which is the equivalent of having the WAL archive. But it also makes all of the data instantly accessible. So the interface to the storage system is what we call the get page API. And the API is basically get page or get the block number 123, whatever, at this LSN. And the LSN is the point in time. It's the log sequence number in the log. So at what point in time do you want to see this page? And that's a very powerful feature because the storage system can reconstruct any page within the retention period. It can reconstruct any page at any point in time, which means you don't need to do traditional like large backups, periodic backups, because the storage system can do that like at the page level. So what you can do very easily is to launch a new compute node also and look at the history of your data. If you wanted to see what did your data look like at 5 p.m. yesterday, you can just start a new Postgres node and you give it the LSN or like timestamp basically, and it will request all of the pages at that older point in time. And now you see your database as it was at 5 p.m. yesterday, which is a very powerful feature. It's very powerful combined if you actually need to do point-in-time recovery, for example, because you can try to find the right point without having to do a heavy restore operation. So the branching is part of that story. If you actually do need to do a recovery, or for example, you would create a branch at that older point in time, and now you can start to write at that. So your history forks at that point in time. So behind the scenes, that's how the branching works. And that's part of the whole backup, restore, disaster recovery story. And it allows you to do this point in time query stuff. Other use case, and which is actually probably more important for like more people use the branching as a developer feature. So the use case is basically that you have a production database, you have a production environment, and maybe you have a staging environment, maybe you have a performance testing environment, and you have a team working on developing your application. Normally, when you're working on a feature for your application, what database do you point your on your laptop or at the hosting provider? Where do you point your developer snapshot of your feature you're working on? Like, where do you do the development? This can be a problem for small, like it's a maintenance hassle. Traditionally, people take backups of their production system or staging system and something, and they restore it locally. And then when you screw up, you have to restore it again and so forth. And all of that becomes a lot simpler with Neon and the branches. So you can, for example, create a new branch of your production database. It's instant. It's like a copy and write system. So you can create a branch of your production system and run some test on it. Or if you want to see how would your database migration work on your production data, you can create a branch, try it out. Very easy and cheap and easy to do. Or if you want to have like each developer have their own copy of the production database, that works. Depending on what data you're storing, that might or might not be okay. But at least if you have some kind of test data, people can share like a master copy of that test data and easily create their own versions of it for their own development purposes. We have some people who have set up a CI/CD workflow, so you have a separate branch of your testing database for every PR you create, which allows you to run automated tests, including database migrations and actually working on the data as part of your CI/CD workflow. So that kind of features are possible with the branching, and a lot of our customers are like figuring out what is the best way to do that, and we're also figuring out like what are all the cool possibilities that you can do with this stuff.
Yeah, sounds pretty cool. One of the use cases that you mentioned, I as a developer want to do some migration or just want to, I'm probably doing some analysis that why my query is slow and is it even using my index, and I want to just play with it, for example. And doing that in production, like understanding the query plan, it's really challenging. I'm always afraid that I might do something wrong. And for example, specifically when you are writing like really heavy queries or even delete queries or update queries, it's really difficult to do that right, and things can go bad. So if I have my own branch where I can work in isolation without worrying about any impact on any customer, I think that's really helpful. And then the other like powerful mechanism that you mentioned or use case that you mentioned for restore and backups is definitely a great thing, because there I have seen examples when there has been a data corruption and we had to restore to a previous state and all of that. But it's always a mess, and it's so much effort and so much cost attached to it. So if I get it for easy way, I think that's game changing for many use cases as well. Talking about branching for development use cases, I so you mentioned that you can create many branches and it's copy on. So
Correct.
what does that mean? Let's go a little deeper and understand what copy on write means in this context.
So it's similar to copy on write file systems, really. So when you create a branch, it's an instant operation. It's like an O1 complexity operation. It happens in seconds. It's basically just a tag that the new branch begins or branched off or forked off at this point in time. So whenever you request, like at the low level, whenever Postgres requests a page on that branch, it will see if there is a page version on the branch. If there isn't, it will look it up on the parent branch at that point in time. So it will look it up at the parent there. That's how the branching works at the low level. So from a user's point of view, it's instant. It looks like you have a separate copy of your database, but behind the scenes, there is no copying involved. It's just a point in time. It's just a label on a point in time, really.
Okay. So it's just that it creates this label, and then it whenever I'm working within this branch, it will make sure that the label stays intact and it doesn't impact any other label or let's say branch. And that's how the isolation is maintained, right?
And when you then write to that branch, it will create its own history of the write-ahead log from that point in time. Like on the branch has the history of that branch has diverged from the parent, so we keep the write-ahead log from that point on where the branch happened for separately for the new branch.
Okay. But at the page level in Postgres, it's all happening within same storage layer. And I'm just giving like different labels to different branches, right?
Yeah, from Postgres, so from Postgres' point of view, the interface from between Postgres and the storage is basically read an 8 kilobyte page. Like Postgres storage works on 8 kilobyte pages,
Yeah.
and the tables or the indexes are stored in these pages, and there's a transaction log for the writes. So the interface between the compute and storage is get page number 123. And the storage system behind the scenes it goes through all of the work to reconstruct the page at that point in time using the logs it has from the parent branch on possibly from the child branch and any possible images you have there. So there's a lot of, and like we've invested a lot in making that fast and making sure that it happens fast enough that you can actually do that on the fly live. But from the Postgres point of view, it looks like just a regular disk. You're reading a page at this offset, and you get an 8 kilobyte page back. And all of the heavy lifting is done on the storage system to reconstruct the page.
Perfect. Yeah, this definitely is very interesting, and I would love to read more about it, like how it's done. That sounds great. And again, the power of separation of compute and storage is coming into the picture. And but let's move on to understanding, for example, auto scaling and how, for example, so as you mentioned, there is one writer instance and one or multiple reader Let's talk about these separately. So let's start with the writer instance, right? So I have one writer instance, there is a storage layer, and I have my writes coming in, it's all fine. But now I get a spike of events or something, I don't know, because of a bug or because of just high traffic or something.
Right.
And then I want to auto scale writes as well. So is it also a possibility because the compute and storage are separate, or how does that work?
So the writes, there's only one writer node, so that is a limitation, but it's not all. It would be rare to have such a high write traffic that one node can't handle it, because what will happen is that we can scale up that single writer node. Like we can add a lot of CPUs and a lot of memory to scale that up. So we have a process that's monitoring the VM, and like in the user interface, you can set the minimum and the maximum size that you want to have for the instance, and because there's cost, we charge you for that, the resources you're using, so you can put a limit on it too. We allow you to currently scale up to 7 CPUs or 8 CPUs, something like that, and the memory size also scales linearly with that. So the idea is that if you have a large spike in traffic in the primary node, we will give it more resources. We will give that primary node more resources. For the reader nodes, you can add as many reader nodes as you want. That's currently not automated, so you have to call the APIs yourself or click buttons to create them yourself. But you can have, that's the way you can scale the read part.
Yeah, as long as I have API, I can automate that. So for reads, I think it should be fine. I want to ask you a question, which is probably a naive question, but maybe I'm missing some details there. So as you mentioned, there is this limitation of having one writer. And I'm just curious, since the storage is separate, why can't we have multiple writers?
Then you get into all the problems with distributed systems. That's the short answer. Like the world becomes a lot more difficult. So at Neon, we run almost unmodified Postgres. Like we have a small patch set, but I'm pretty happy with the size of that. It's not large, it's 1,000 or 2,000 lines of code. And we like to keep that way. Like people want to have just Postgres and not a different version that has different trade-offs and so forth. If we would support multiple writer nodes, that would definitely go into the category of you have a different trade-offs. Like suddenly you have to deal with the conflicts. How do you ensure the consistency between the nodes? At what level do you separate by table? How do you shard it, or so forth? And there are systems that do that, but they look different. They're not Postgres anymore. They are something different. And there's a lot of systems that do that and research, but we haven't gone into that world. Also, like it tends to be like then it depends on the workload. If you have like scaling the writes out doesn't really help if all of your data, or if the bottleneck is one account or one customer or whatever. So often you would have a bottleneck even in such a system. The scaling up the single the primary nodes helps a lot with that, because you can digest quite a lot of traffic with a single node of Postgres. And it also actually helps that you can have the read-only nodes to handle the read traffic, because even in many applications, a lot of the traffic is coming from the reads anyway, and if you can offload those to the read-only nodes, it like relieves the pressure from the primary as well.
I think it's fair enough. If we are using Postgres the way it is, I think it makes sense. And just to give you a little context, like where this question was coming from. So I've seen it like in the history of different databases that were developed over the time, like all of them were at some point in time using Postgres, and then Postgres were not able to scale for certain workloads, for example clickstream or time series data and all of that. And mainly it was mainly about the number of writes they wanted to do. So I was thinking if we could separate that out, but as you said, that's not the problem Neon is trying to solve.
Right.
And that's fair enough. I think I have a good understanding of the separation of, let's say, compute and storage, probably at a high level as well. But let's move on to the other feature, like you mentioned, auto-suspend. And I guess this is where you can make it cost effective. But let's describe, what does auto-suspend mean? And is it just taking down the compute nodes, or there is more to it?
So auto-suspend means that if you're not using your database for 5 minutes or whatever timeout you set, then we kill the VM that Postgres is running in, and we keep the storage alive. The storage is always there, and there's like a multi-tier system where the old data and less frequently accessed data is uploaded to S3 and kept there in colder object storage. But the basic idea is that we don't keep the VM running, and that's where the cost savings comes from. So we have hundreds of thousands of databases under management, but only a fraction of them is active at any given time. And the auto-suspend lets us do that, and that's also the secret why we have a pretty generous free tier, and that's why we can afford it, because in practice people come in, kick the tires, but most of the databases are not active. So that allows us to keep them dormant very cheaply. But they are there, like whenever someone tries to connect, we have a proxy in the architecture that kind of all of the connections go through the proxy, and the proxy will do the whole dance with the control plane. Is this running already? If it's not, then you launch it. You take a VM from the pool of VMs, you initialize it with the right data of that database, and then you forward the connection to that. And we've made that happen in under 1 second. There's an interesting story actually behind that. Like when we were starting out, the cold start latency, as we call it, was larger. So we aimed for bringing up the VM if it's currently stopped online in under 5 seconds. And so when we started, that was our goal, and that was the reasonable thing we thought we can do, and that worked fine. Like we got it under 5 seconds, but So this was roughly a year ago. But we got a lot of complaints. Like people were complaining, like great product, but the cold starts are horrible. That's too slow. It's painfully slow. So we had partners complaining, what are you going to do about cold starts? We had users asking about that. And people were asking, how do you disable the auto-suspend? Because they didn't want that. Like that 5 seconds was too much. So we put a lot of effort into that. Like we made it a company priority that we need to get the cold starts latency down. That is clearly too much. Like 5 seconds, to me, it doesn't sound like a lot. If you haven't used the database for more than 5 minutes, is 5 seconds really is that a big deal? But apparently it is. So we put in a lot of efforts and we added a lot of instrumentation to the cold start. Like where exactly is the time spent? Like how much is going into the TLS handshake with the client? Then how long does it take to start the VM? How long does it take to launch the Postgres process inside the VM? And then it downloads the initial catalogs and other stuff you always need when you're connecting. Like we instrumented and got the metrics of all of those pieces where exactly the time is spent, and we started to shave away all of the parts. The biggest saving came from having a pool of VMs already pre-launched. So we maintain a pool of VMs that are not tied to any particular database, but it has all of the software loaded, and it already has the Postgres process in memory and like all of those pieces. So when a connection comes in, we can just take a pre-created VM from the pool and forward the connection to that. So after doing all of those things, we got it down to under 1 second. I think your average is around 700 and 800 milliseconds at the moment. And that was good enough. Like we don't hear those complaints anymore. We have a roadmap of plans to get it down further. Like we think we can get it down to 300 milliseconds or so. But it looks like it's mostly a solved problem now. So the complaints stopped. So it seems that there is some kind of psychological threshold somewhere between 1 and 5 seconds where people have the time to think, hey, this is slow before it starts up. When you're at the PC equal prompt, somewhere between 1 and 5 seconds seems to be where people think about it.
Interesting. And thanks for sharing that. That was my next question. Like, whenever you take down the compute, cold start could be a problem, especially like talking about databases. And it's amazing that you brought it down like below 1 second, average 700 millisecond. That's amazing. For my workloads, I think I would be fine anything below 1 second. That sounds great. And you also mentioned that the majority of the improvements came from like having a pool of compute nodes available, and so you just have to then connect to a specific storage node and then you're good to go. At what level these pools are maintained? Is it also like specific to a cluster, or how is that organized? How do you figure out like what is a good pool size? So because it's a trade-off between cost and then being consuming all the nodes that you have in a pool, so how do you balance that?
That's a good question. So there's a bit of art and science behind that, and that's something we keep optimizing. Like we keep looking at the graphs and statistics, but we have a pretty basic algorithm now that like looks at how many VMs have launched in the last 5 minutes, minute, an hour, and makes a projection based on that. We can also see there's like clear spikes in certain times of hour. There's applications that apparently ping the database once a minute or once an hour and so forth. So you can see those things come up, and we can predict those spikes pretty well nowadays. But at the end of the day, it's just a matter of having a large enough pool that you can take the spike. We try to keep all of the VMs the same, and that's also why the auto scaling is important for us. So we don't have different instance sizes; they're all the same. But then once you've taken it from the pool, then we can size it to the maximum capacity, or like to the right size that you want for that instance. But when it's in the pool, when it comes from the pool, they're all the same size.
Interesting. Yeah, that is very interesting as well. I think you also mentioned logical replication, like how you have more replicas and you scale your reads basically. And you also mentioned there's technically no limit, like you can have as many read replicas as you can, as you want. And then, but does it in a way end up also impacting the primary node, or it's completely separated out?
So firstly, it's physical replicas is what we do with the store at the storage level. We're working on logical replication, but it's still in beta but that's more for interacting with like replicating in and out of Neon to other systems and doing stuff like replicating only a single table. But the fact that you can have multiple read-only nodes, those are physical replicas. So yeah, you can launch a physical replica. It doesn't affect the primary. We have a separate component called the safekeepers, which actually run a consensus algorithm, and that's how we guarantee the durability of recent transactions. So when the primary nodes, when you do a commit on the primary node, it makes sure that it's present and on a consensus between at least the 3 safekeeper nodes always running. So it makes sure that it has made it to at least 2 of them. But we also leverage that in the read-only nodes. So the read-only nodes don't read directly from the primary. They actually connect to these safekeepers, which take care of the transaction log, and they're streamed through that. So it doesn't affect the primary. They do hit the same storage nodes, but at the storage level, again, we can scale the storage separately. So if there is a large, if there's a spike of load in the storage level, like we can add more capacity there in the storage level, and that's invisible to the application and invisible to Postgres.
Interesting. Going to the storage layer a bit more, like I want to understand what exactly is running there. Is it like good old Postgres, only the storage layer? How is that separation working, and how does the data get stored? For example, if you talk about like ingestion of data, I'm writing something for a transaction. Where is it stored, and how does that gets replicated? What are some details there?
Right. So I mentioned the safekeepers and the consensus algorithm. So that when you it all works with the write-ahead log of Postgres. So when you commit a transaction, when you do a load of data, whatever, it goes to the write-ahead log, and the consensus algorithm makes sure that we don't lose it. Like that's the first line of defense that makes sure it's durable. Most of the complexity is what we call a page server. So from the safekeepers, the log is streamed to the page servers, and the page server digests the WAL. Like it looks at the WAL stream at every record and figures out what page does each WAL record modify. And then it splits apart. So normally the transaction log is like a sequential, you append to the end. But what we do is we reshuffle the log so that we keep together the log records of every individual page, so that when we get a request to reconstruct a particular page, like block number 123, we have all the WAL records for that particular block together, stored together. So internally, there's an LSM tree-like implementation that we wrote from scratch that is good at digesting the writes, like digesting the log stream. And then there's a lot of heuristics and code to reconstruct pages of these based on the transaction log and some previous images of each page that you have. So this is all written from scratch. Like this is all written in Rust. Like it's a completely separate piece of software. It doesn't use Postgres code, except there's like one exception is where we replay the WAL record format. So we reuse the Postgres code there, but there's a little sandboxing thing where we run a small Postgres process to do that. But other than that, it's all written in Rust, and it's written from scratch to be a multi-tenant service. So that allows us to share the data from all the different users, all the different databases in the same storage system, and share the resources.
That adds up to the cost optimization at the storage level, because
Yeah.
you're able to share. Okay, interesting. It's very interesting that it's written from scratch. And what controls or what ability apart from cost optimization does that give you?
The branching I mentioned, like that's an integral, like the reason that we have the separate storage system allows us to do that. So the storage system understands that the concept of branches and can do the garbage collection and all that, taking the branches into account. Then there's the fact that you can connect multiple read-only nodes to the same storage. Like you could imagine taking Postgres and putting your disk on an EBS volume or something, and that would be separation of compute and storage as well. Like you have the disk somewhere else, but that doesn't give you the other benefits. Like the storage system needs to understand a little bit about the format, what is a page, and how to reconstruct the page, and so forth. Because then you can do these things like share the storage between the different nodes and so forth.
Yeah, very interesting. I also heard LSM tree somewhere in your explanation. How does a LSM tree help you? And did you use some LSM implementations like RocksDB, or what was your thought process and decision making there?
Yeah, that's a good question. We did not. It's written from scratch. Like we wrote that thing. we spend a lot of effort on that, and this is actually something where if there's any LSM3 researchers out there, I would love to hear opinions and get help maybe. But the thing that's unique to our implementation we have some unique needs. So I said that we keep all of the history, so that's slightly different from normal LSM3 implementations. Like RocksDB, for example, they have a concept of snapshots, and so you can have a snapshot at that point in time, and you have a consistent view of the data at that point. But we do that at a much bigger level. So you can keep like days and months of history, and you can even after the fact, you can have a query where you want to see a consistent snapshot of any of that data at any point in time. So we didn't find any LSM3 implementations that would do that. The kind of other special things that we have is that we are not just like updating a key value and replacing an old key with a new value. We're keeping the val records, which are already like deltas between two versions of a page. So we both needed to take that into account, but also take advantage of that. So we don't need to store, or we don't need to materialize the 8 kilobyte page at every record, but we can just keep the record and apply it on the fly. So we didn't find an existing implementation that would do all of those things. We actually spent a lot of time thinking about, could we take an existing LSM3 implementation and there's a lot of open source implementations out there and modify them. But we didn't want to do that either, because we wanted to, first of all, we're writing this as a multi-tenant service, so security is a big thing. So we would need to be a memory safe thing. We couldn't find a good library or a good existing implementation that was written in Rust or other memory safe languages that would do what we want. We could take something as a starting point, but we would have to modify it so much that I wouldn't trust my coding skills to make that safe in other languages. So we ended up writing our own.
Yeah, fair enough. Let's talk a bit about fault tolerance. Read replicas, I think it should be fine because I have multiple of those. And if one goes down, probably a new one will come up, or probably I have to automate that using the APIs. But for the writes, what if the primary goes down, and how does that work?
If the primary goes down, you launch a new one. That's the neon answer. You can do that in under a second. So that's not a big deal. That's the basic answer. There is so to the user, that's all invisible. If the primary dies, you just create a new one. But how do we ensure the consistency at the storage level? And that's where the safekeepers I mentioned come into play. So there's three separate safekeepers running for each branch, and there's a consensus algorithm there that ensures that you have at least you don't acknowledge the comment until you have it in at least 2 copies. That ensures the durability. Then after that, what happens after you've done that, that's just the first line of defense. Then we rely on Amazon's S3, object storage at the moment, for the long-term storage of all the old data. And if you have a large database, most of the data ultimately lives in the object storage. And kind of our storage systems, you can think of it as just a cache over the object storage too. So ultimately, that's the source of truth if something goes down.
Yeah, I think the compute and storage has made it a lot easier. At least understanding that if your primary goes down, you get a new compute, which is fine. Do I also get this from the pool, by the way?
Yeah.
Okay, perfect. Okay, nice. And then at the storage level, you have the safekeepers, which keep the data consistent and make sure you're doing the right thing. And that is interesting. And so the safekeepers, are these like separate components, separate from storage layer, or these are like within the storage layer, or how is that topology looks like?
So the topology is that the Neon storage system consists of 2 components roughly, and there's some others to manage this all, but it roughly consists of 2 components. It's the safekeepers, which manage the durability aspect, like that, and they run the consensus algorithm. And then there's the page server, which does all of this LSM3 stuff. So with this separation between the safekeepers, which handle the durability of recent transactions, and it's all about high flow of traffic, high flow of transaction logs, and keeping it safe, running the consensus algorithm. And then you have the page server, which doesn't have that kind of durability requirements. If one of them dies, we can just launch a new one. That's a slow process because it will then need to download a lot of data from the object storage. But from a consistency and durability point of view, that's easy. Because all of the data is durable either in the object storage, and the recent data that you haven't uploaded there yet is present in the safekeepers. So this has allowed us to develop this thing pretty fast, because we have a separate team working on consensus, keeping the recent data safe, make sure you don't lose the recent data, and a separate team working on long-term storage, like I/O capacity, and all of kind of different problems working on a different team working on different problems.
Yeah, that sounds good. So it's again like a different component. It's all written from scratch, like also the safekeeper.
Yes.
Okay, perfect. Since we have this LSM store and the page server, whenever we talk about LSM, there's always compaction happening in the background. And I've also seen, at least for some write heavy workloads, compaction might create some problems. How is Neon dealing with that?
Well, we are putting a lot of resources into that. It's true. LSM trees are the compaction, and when do you do that? How do you do that? That's critical for performance. We are actually in the process of rewriting the algorithm we are using at the moment, and we'll see. Like the short answer is that we have a lot of work to do there, but it's not visible to the users. It's just that we are suffering ourselves because it's consuming more resources than it should. But that's definitely an area that we are still working on.
Perfect. Awesome. I think it's pretty much clear, like at a high level, how the architecture looks like and what is the benefit of the compute and storage separation and in different aspects, right? In failover, in scaling, and in branching and cost optimization. And it looks really powerful. From the use cases perspective, what are the, if you talk about the real world use cases, what are some of the most common use cases that benefit from Neon? Probably some case studies out there.
Yeah, the most common case is that like the developer productivity thing. Like you need a database for your application and you need it quickly. Neon is very easy to get started with. Like click a few buttons and you have a Postgres database, and now you can start to write your application. Then all the branching features, like all of that adds to that. Like you can easily create your production data, your copy of or branch of your production database and do tests on that, and the CI/CD workflow, like all of that's the majority of our users, I would say. Then we have a few big partners. I mentioned Retool, the Railcell, Hasura, some others who are using Neon because they have a large fleet of database and they're offering or reselling a Postgres database as a service to their users. And Neon is good at handling that kind of large fleets of small databases. There's a third use case, which is rare, but we have a few customers who are actually using the branching capability as part of the application. So the typical case is like the common scenario is that you're doing some kind of scenario analysis. So you have your database, and then you wanna in your application you wanna tune some parameters or some starting conditions, and you run a simulation on and the way your application does that is does a lot of updates and selects on your database. And they're actually we have a couple of users customers who have integrated that workflow into the application. So they use Neon's branching, like they call the branch APIs directly from the application when you start a new simulation, and then you can keep the result of that and see what the database looks like after that. So those customers find the branching super valuable, and it's a unique capability that is hard to do with other databases, but that's a fraction of the use case. The most common use case is the developer productivity. If you're writing a JavaScript application, serverless application, Neon is a good fit.
Yeah, that makes sense. Since we are talking about developer productivity, let's talk about from the what changes for the developer. So let's say a developer is using like an old Postgres database versus now wants to migrate to Neon. How does that experience change? To start with, in the beginning, I mentioned two use cases, like one enterprise and one I'm just trying to prototype something and I don't have a ton of data. But for the enterprise use cases, let's say I want to migrate over to Neon. How does that the bulk upload or the backfill of the database work, and what do I have as a developer in terms of tooling?
At the moment, that's a case of you dump your production, you dump your database and you restore it in Neon, like just using regular Postgres tools. There's pg dump and restore if it's not too large. There's ETL tools to do that. We don't provide anything special currently. We're working on some tools, and the logical replication, which is coming up soon, will help with that. But that's basically what you do. You dump and you restore in Neon.
Okay, that sounds good. From the migration perspective, of course, one is that you like these flyway migration. You update your tables, add index, and remove some columns or things like that. What kind of support do we have when it comes to tooling? It's just like everything that works with Postgres work with Neon, or there's some limitations or some added things.
Correct. Everything that works with Postgres works with Neon as well. you get the extra benefit of the branches again. So that gives you more flexibility in testing those migrations, and it makes it easier to develop. But we're agnostic to the tools. So whatever tools you're using with your Postgres database today works the same with Neon.
Perfect. And the other part is if I need, let's say I need some fancy extension for my vector search or full text search, I assume that also all works with Neon because it's Postgres. Like the experience doesn't change, right?
Correct. We have PG Vector, we have full text search, we have all the other popular extensions that people ask for, like we bundle them with Neon. The kind of the architecture that we plug into Postgres at a very low level, like at the point where you read and write 8 kilobyte blocks, basically. So that means that any new data types, any new index types, they generally just work. As a rule of thumb, anything that works with Postgres replication will also work with Neon because it goes through the same transaction logging and all the same machinery.
Okay, perfect. One problem I have faced, at least in my experience, like at least using Amazon Aurora, is that for database upgrades, like version upgrades, specifically major version upgrades, you have to do. There are so many moving parts. Like I have to. There's downtime. I have to take down the cluster, shut down my applications, then do the upgrades, and then probably do some other stuff, and then bring a new cluster up, and then restart my application. How does that work with Neon?
So the answer is we haven't done anything special. So we support versions 14, 15, and 16 at the moment, and 17 sometime in autumn when it's released. We've been working on supporting PG Upgrade, which is the Postgres tool. It's not implemented, so that's still in the roadmap. I'm hoping to get to that sometime later in the year. I've actually been surprised how few people ask for that. So like we've been running for a couple of years now, and we have a handful of requests for people upgrading from 14 or 15 to 16, which surprises me. I guess people are very happy with those releases, but I'm sure we will have to work on that. But we have I believe we will have a good story because you can actually, with Neon branches again, you can practice your upgrade. So the way it will work is that there's a button to do the upgrade, and it will run PG upgrade for you, and you can do that on a branch. You can, if you don't like the result, you can go back, fix stuff on the primary branch, try it again, and all that can be very fast. But that's, as I said, that's still in the roadmap.
Okay, but let's assume that was implemented. So
Sure.
branching ability would help me do the zero downtime deployments, right, or upgrades.
It won't be
That
zero
would be
downtime.
possible.
There will be a small window, but
Yeah.
most people are happy with a small window. The way to do a truly zero downtime upgrade is to use logical replication, which works, and I'm sure we will have documentation on how to do that as well. But that's more complicated because it actually involves setting up both systems at the same time and managing that. And you do end up actually copying all of the data in that case. Like with the PG upgrade approach, you don't need to copy the data. It's just you only need to rewrite the catalogs, which is a relatively quick operation. Like I would imagine that most databases would be less than 5 minutes of downtime.
Okay, perfect. I think that gives like a good understanding of how Neon works internally up to the storage level, how the architecture looks like, what are the high level features. And I'm really excited to try these features. But
Please do.
then, since I'm really excited and I also hear the free tier thing, because when I'm prototyping, I would love to use that. Tell us more about the free tier. Like, how can folks go and use the free tier and what they have to do?
So you go to the neon.tech website, click a few buttons, and then there's a guide on how to do that. Like it will guide you. Go to neon.tech and sign up. That's how you get started. So what you will get is a Postgres connection string, and then you can use whatever Postgres tools you have to work with the database.
Okay. And how does that multi-region deployment work when it comes to Neon?
Currently, we have like you choose a region. So when you're setting up a database, you choose a region you want it to run on, and then everything happens within that region.
Okay. That is amazing. You have already mentioned like some of the things that will be coming up in the future, but I'm still curious to know like what is in the roadmap and what are you currently like
Right.
actively working on?
So I think what excites me the most is actually like we have all the fundamentals in place. Like we have the separation of compute and storage. All of that works, and we've been working on that. What we are now working more on is the kind of user interface and polish, and like people are using the branching capability, all these amazing developer productivity things I've mentioned, but we don't actually provide a lot of guides on how to do that. So our customers have figured this stuff out on their own without much guidance from us. And what I'm seeing is that the customers who have done that, like the users who have gone through that and figured out how to use them, like they're very happy. Like they love the product. But we have a lot of users who don't get to that aha moment. Like they start to use it, but they can't figure out where exactly, how do you integrate this into your CI/CD workflow, and how do you actually set up your production staging systems? How do you do this testing of migrations? And so that's actually what excites me most. Like we're putting in a lot of polish into all of that stuff and providing more guides, more helps on how do you actually use the product, how do you use the branching features. And I'm looking forward to get more people more quickly to that kind of aha moment where they get it and see the value.
Yeah, absolutely. That will definitely reduce a lot of friction when it comes to onboarding onto Neon database in general. And I think I've learned a lot how Neon works, and I'm really excited. I really have a project I've been working on side, and I think Neon, I can try it out and play with it more. And I'm looking forward to the future developments that you do and you release. So really excited and looking forward to it. Thank you for joining me today and giving me all the information and insights and explaining how things work. And looking forward to more collaboration and more episodes probably on Neon future roadmap.
Thanks for having me. And if you run into any trouble with your database, give me a ping.
Absolutely. Thank you.